5G antenna design will be vastly different as we transition from 4G to 5G. From the interface between the antenna and the radio frequency front end, the use of arrays instead of single antennas, and the use of beam steering. Just how different will it be? Here to tell us is James Kimmery. He's Director of Product Marketing for RF Communications and Software-Defined Radio, that at National Instruments. And James, welcome to the program.
Thanks, Ed. Thanks for having me.
Well, thanks for being here. I want to get right into it. What would you consider, just sort of right off the bat, would you consider massive MIMO to be a revolutionary idea, and why?
Yeah, it's definitely revolutionary. If you think about today's networks, a traditional base station and a 360-degree geographic area, 120-degree sector, and that sector may have 6 or 8 antennas, probably 6, and that topology really hasn't changed in the last 20 plus years. What massive MIMO attempts to do is to increase the number of antennas per sector to hundreds of antennas, 128, 256. And because there are more antennas for a particular geographic area, the actual electromagnetic energy, or the beams, they can actually be pinpointed to individual users. That also increases the data throughput, but it also saves on energy consumption because you're not blasting energy indiscriminately across a wide geographic area. So it has the potential of increasing data rates, but also improving energy efficiency.
Now, of course, we're seeing really the doubling of integration density, going from 2x2 MIMO to 4x4 MIMO. Can you kind of walk us through that trend?
Yeah, well, in terms of spectrum below 6 gigahertz, spectrum is a scarce resource. And so what we want to do is be able, or what the industry is going toward, is to be able to get more bits for the same spectrum, so to speak. And what we call that is spectral efficiency. And a typical way to measure that is bits per second per hertz. And so by increasing the number of MIMO streams and using a concept called spatial multiplexing, we're able to increase the spectral efficiency for a particular network. And so you've seen MIMO be used in 802.11 as well as LTE for many years now. And that trend for 5G is expected to increase dramatically with concepts like massive MIMO.
Of course, there's a lot of talk around beamforming. What's the significance of beamforming, and what advancements have been made over the last several months or years even?
Well, that kind of goes hand in hand with the massive MIMO concept. The reason that massive MIMO is able to achieve, some of these spectral efficiency gains is because of the concept of beamforming, able to really direct the energy to the particular users, and having the users also in concert be able to utilize the uplink and beamform in the uplink as well. And so that digital beamforming in particular has been around for quite a few years. It just really hasn't made it into commercial standards, and with 5G and massive MIMO, it has that opportunity. Now, for millimeter wave and frequencies above 6 gigahertz, new concepts called hybrid beamforming are being investigated and actually being prototyped. Some of our lead users are actually utilizing those techniques and these concepts called phased array antennas. And what hybrid beamforming is, it's a combination of digital techniques, which you would see at massive MIMO below 6 gigahertz, and using analog techniques at the antenna itself. And so by using a combination of digital techniques and in terms of real-time signal processing and analog techniques, we can get a better coverage as well as increased throughput for millimeter wave, and specifically frequencies 28 and 37 and 39 gigahertz, which are being considered for 5G deployment.
So what industry is really familiar with is 2x2 MIMO moving to 4x4 MIMO, and that doubling phase as we move towards 5G. Is it 8x8 MIMO, and is that already being deployed out there?
Well, LTE release 13 proposes 8 by 8, I believe, and they also introduce these are 4G standards, 4G evolution, and then there's even concepts up to 32 antennas in 4G today. Whether they are actually implemented or not, I think that's on a network by network or carrier by carrier basis. For 5G, almost from the get-go, kind of the baseline is what they call component carriers and carrier aggregation, which is not necessarily a form of MIMO, but some of the concepts are the same. It's the idea of increasing the number of channels for a particular user, and that increases the data rates. For example, if you have 20 megahertz or bandwidth or for one particular channel in one area of spectrum and another free area at 20 megahertz in a different part of the spectrum, those two spectrums can be, or the channels can be aggregated to essentially increase your throughput. Now with 8 by 8, that would essentially potentially increase bandwidth per user or for the network by as much as 8x.
I know there's a number of real-world deployments for 5G out there, but really the trend again is now really full-scale 5G test beds. Can you tell us more about that and where those might be located, or where can we expect them?
So there are a lot of challenges with 5G, and I think one of the biggest challenges is typical design process would stop at simulation for a lot of the initial work. So, for example, a researcher or a company has an idea for a concept. What they would do typically is create a math model and create a model of the network and basically simulate that. With 5G, that modeling approach really can't be used. The simulation alone, it actually has to be prototyped. And if you think about the challenges of 5G in terms of increased data throughput, increasing the number of users on a particular network to maybe, or a particular node to be millions of nodes connected to a single base station, those types of things really can't be simulated and effectively. And so the industry as well as academia, they're looking at building these test beds at scale, which means instead of simulation, actually building some of these and improving these technologies in real world conditions in a real world environment. And so specific initiatives I think that are public, Bristol University, the city of Bristol in the UK, they have an initiative called Bristol is Open. That is a citywide 5G-like network that they've been working on for several years, and incidentally, some of our massive MIMO technology is actually being deployed in that test bed. And then most recently, the NSF and the White House Office of Science and Technology Policy have proposed for the United States building 4 city-wide or city-scale type of test beds in the United States at four locations. And this is kind of a different approach that the National Science Foundation has taken. Instead of funding 1 or 2 researchers, actually funding a group of researchers, and also designating specific municipalities and cities and universities for deployment of these technologies. So that's actually pretty exciting that the industry as well as government policy, they see the need to be able to actually test and prototype these systems in real world conditions. And I think that's critical to moving the 5G agenda forward.
James, it wasn't long ago that you attached the phrase the valley of death to something that you're experiencing maybe between academia and industry right now. Can you explain that to our viewers, what that means?
Yes, kind of somewhat related to the previous question in terms of government policy and actually and academic research and industry. Right now, industry has a short-term focus. It's very difficult for a publicly traded company to invest in longer-term research projects. Every quarter, the financials are looked over and assessed, and so those investments in research are heavily scrutinized. And so for long-term innovative research, those projects they seem to dwindle. And then And then you got the academic side where, you know, they come up with just amazing, brilliant ideas, but yet they never make it to the product stage, right? Maybe they publish a paper, maybe they build a small prototype, and that's where these initiatives like the NSF Power Initiative, Platforms for Advanced Wireless Research. That's what that program is really and aimed at trying to address. So it's the Power Initiative, as I mentioned in the previous question about building these test beds at scale. They're going to build 4 test beds, and it's not just the NSF and the White House OSTP, but also 26 industry companies. And the idea is by pooling these resources together and actually building these test beds at scale, we can really address this valley of death between academic research and commercial research.
James, I think as these test beds at scale become more prevalent, we'd like to circle back with you and get your input on that. So love to have you back on the program.
I'd love to come back, Abe. Thank you.
Thank you, James.